So hello, my name is Erni Durdevic. I am a machine learning engineer at Quby. And first of all, I would like to introduce you a little bit to what is Quby and what we work for. So at Quby, we believe that the future can be better. It can be easier, more comfortable, and more sustainable. And that is why we want to help households and homes to make this transition without compromising on the important things in life. But let's take a look at the problem that we want to solve. Worldwide, there is more than 100 trillion kilowatt hours of energy consumption. So this is everything combined. So it's our fossil fuels, our carbon, coal, gas, electricity, and everything combined. So if we want to make a world more sustainable in the future, we have to address this issue and change the way that we produce energy, but also the way that we consume energy, and make it more sustainable. So if we take a look in Europe, what is happening inside the houses, we can see that 44% of all the gas that is being used in the houses is being used in our houses and not everywhere else. While 27% of all the electricity that is being used in Europe is also used in the houses. So what we wonder is how much of this is actually wasted. So what we want to do, we want to enable houses to be more efficient in this energy that they use. And this is the amount of impact that we can make. This is where we can have this impact. So Quby is a technology company. We are based in Amsterdam, and we partner with other companies like energy providers, banks, or water companies. And we help them deliver to their users the technology and the services in order to enable a better use of energy, water, and gas in the homes. So you see on the left side, you see our flagship product, which is Tone or Box in other countries. And it connects with the apps, and it helps users to save energy in their homes. And also it is able to control the temperature in the house, being a smart thermostat. Let me take you through what is the data that we use, because this is a technical talk, of course. So I want to see what actually we do use and do with the data. So we have a smart thermostat. It's in our houses. It's connected on the wall, and it's connected to the central heating system. So we do control, but we also read some data from it. We know if there's an error code or what are the temperatures of the boiler. And then we also connect with all the water sensor, gas sensor, and electricity of the houses. So we can see in real time what is the energy consumption of that home. We also connect with solar panels, with storage, with Z-Wave devices like smart plugs and smoke detectors, and also a series of third-party apps. So Tone is our central hub in the home, and we collect all this data, this IoT data, and we provide services on top of that. So you have seen a little bit of what we do. We will see a little bit what are the services that we deliver and what is the technology stack behind it. So generally, all the services that we build more or less look like this at the high level. So there is some IoT data, we run it through some ETLs and models, and then we deliver an outcome to the user. So as you have seen, we have a variety of different IoT data, and in order to process them, refine them, we run more than 60 ETLs end-to-end to deliver these services to the user. And then we have the models, so the core technology of our system. And I represented here what are the types of model that we use. So you see there is a great variety of different models that we use, and there are two big families. So the first one is offline training. So offline training are models that we train once on our data, and that they can be reused every day for all the households. For instance, if we have a model that can detect the charging of an electric vehicle, we don't expect this to change over time. So an electric vehicle will look more or less the same in the next few years. So we train it once, we deploy it, and we run this on all our users, and we get the detections out. But we also have some dynamic models. So for instance, the behavior of each user changes every day. So if we want to model this behavior, we have to run a model for each one of our users, for each one of their appliances every day, because this can change over time. So this is how we have a set of offline models that are generic, and more specific, which are user-based or for a group of users, and that we need to keep track of and maintain over time. And finally, we deliver an outcome. So we reach out to the user and we say, hey, look, your washing machine is inefficient, but actually is efficient, but your dishwasher is inefficient, or your dryer is inefficient. So this is how we reach out and we deliver these products to the users. But let's go a little bit more in detail in the technology stack. So this is the core of this talk. This is the end picture that I want to drive you through. So we have a central data lake where we send all our data, and then we run batch streaming and R&D on top of the same infrastructure. So I'm going to walk you through step by step to this picture to understand exactly what is in there. Let me start from the start, right? So at Quby we delivered the smart thermostat in a lot of homes, and we started to collect data. And we had to decide where to put this data. So this was 2.5, 3 years ago, more or less. And we decided to put it on S3. So S3 is a distributed file system on Amazon infrastructure, but we needed some kind of abstraction on top of the tables that we were storing, so we used Hive. And Hive provided some partitioning capabilities that helped us to solve this issue. So once we were there, we had to choose an infrastructure where to run it, and we wanted to use Spark because we had a lot of data. And at that point, we chose Databricks in order to provide the clusters and the infrastructure to run all our services. And first thing that we did is we started to analyze do some batch processing on top of our data to deliver these services to the user, and then we send it to the services. So you see, the batch processing takes the data out, does some refinement of the data, and stores it back to Hive. And then it reads it back again and maybe combines with other data and stores it back to Hive until the data is refined enough to be comprehensible to the user. And at that point, we send it to the services API. So since the services API cannot query Hive because the latency is too big and the concurrency is almost non-existent, we need something that can really serve fast this data to the user. So the service API usually is responsible for their own data store, but it's small data, it's not that big at this point. Let me show you an example of what I mean. So for instance, we have noticed that some people have a schedule for their thermostat, but sometimes they are not at home while their house is still being heated. So we wanted to help them to create the best possible schedule in order to have a comfortable home, but also save on energy. So given all the data that we gather, we want to provide a schedule advice service in which we can suggest some changes in their behavior. So if we take a simplified look at what is happening. So if this is the data pipeline, you see that we gather some raw data and we refine it a bit. And then we store it back, and then we refine it a little bit more, and we store it back, and so on. So this way we can always take a look at what is happening in all the stages and have a backup point so to look at what is in there. But from the engineering point of view, it's also very nice that all these data transformations have data as an input and data as an output. And if you look at it with engineering eyes, you would see that it's a great fit for unit tests. So how do we run our unit tests? It's a simple snippet of code. It does nothing but filtering the negative values. But you see, the important thing here is that you have input data and output data, and nothing else. So no side effects or no other parameters. Data in and data out. So with this paradigm, it's really easy to write a unit test. So this is Spark code in Scala, where we have some input data and output data and run through it. And here there are a few tips. If you're running unit tests on Spark and you want to make them faster, I really suggest to look into that. But once we have this abstraction, so data transformation, data in and data out, using Spark, it's also very easy to go from batch to streaming. So what changes in this transition? Actually, most of the things that you are used to with batch processing also work in streaming. So you can do selection of data, filtering, and you can also run group by joins, join stream to stream, or join stream to batch table. But what you cannot do non-time based window functions. So if you want a lead or a lag on a value, so differentiate a signal, for instance, this is not possible. So you have to fall back on time-based windows, which is a little bit more, it's a different paradigm. So you have to think a little bit on how to re-implement this for streaming. But most of the things, I would say, just work out of the box. And another nice thing about this infrastructure is that if you have all your jobs that are chainable, you can also run an integration test end-to-end. So you can mock some data as an input and then check what comes out of your pipeline. So this was about how we run batch processes. So we started to gather more and more data, and we started to get click data or data coming from SQL. And of course, we also had our data scientists exploring the data on their notebooks. So this is all in the Databricks platform. We have the exploratory data services, and our data scientists just log in, create their own cluster, and query the data that we have on Hive. But they started to build more and more models. So at a certain point, we realized that it was difficult to keep track of all this model, all what was tried, what worked, what didn't work, on which data it was trained. So this is where MLFlow came in. So at a certain point, we decided that this is the way we want to go. But what does it mean? What does MLFlow provide? So if we take a look at this is some Python code that you can use to train a model. It's an example. So if you have this code already to train a model, adding MLFlow is as easy as adding 3 lines of code. So with an experiment start, MLFlow defines this concept of an experiment, and you can log parameters. So what are the parameters that you use for your model? What is the artifact of your model? And what are the metrics? So the precision, accuracy, recall, everything you need. And you can just log them as you see. And on the side of the notebooks, you will see all the list of the models that you have trained with this notebook. And if you're using Delta, you also see the time in history, what the data looked exactly at that moment where you train your data. And once you have a bunch of these models trained, perhaps you use a grid search to optimize all the parameters. Every parameter was logged. And you can go to the MLFlow UI, and you can find some nice graphs that can help you understand which are the best models that you have trained. So for instance, this is a parallel coordinate plot. And you can select some level of accuracy and see how this maps to all the parameters that you use to train the model. So for instance, we have plotted here the train accuracy, the test accuracy, and the model size in kilobytes. This was a random forest model. So you have a max depth, number of tree, and max bins. As you can see, as you select different models, we have seen that max depth of 20 works much better than shallower trees. But let's continue our journey as a Quby. So everything worked fine till this moment. So we could use Hive and MLFlow to track all our models, to deploy to production, to run our jobs. But when we had the need to implement some real-time services and streaming in general, this didn't work anymore. So we could stream data out of S3, but streaming data out of S3 is very expensive because you have to list the files for every batch that you process, and Amazon charges for that. So we had a nice surprise in our build. But you can also attach some queue on top of S3 and get the data out of the queue, but you can consume the queue only once, and we need more than one stream out of the data. So the solution that we chose, which was the most obvious at that time, was to switch Hive to Delta. So Delta Lake provides both streaming and batch interfaces. So there is one core difference between how Hive works and how Delta works. And if I want you to bring something home, it's just this. Apache Hive doesn't have a transaction log. Basically, it handles, it has an atomicity of the transaction by copying and moving some files from one temporary folder to the actual folder. But it doesn't have a log. Well, Delta Lake has this very powerful and simple concept of abstraction, which is the transaction log, which enables time travel. So you can query the data as of yesterday or a month ago. And you can also see everything that was added and appended, so you can scroll through it and get the log of all the new files. And also, it helps with data locality because it adds z-ordering and file compaction on top of the basic partitioning that Hive has. So if I want to condensate the learnings that we had while developing these pipelines, I would say that the first thing is enforce idempotency constraints. So always have a function, a transformation function that given an input delivers an output. As simple as that, no side effects. And second, let the data transformation be chainable, because once you have defined all these small components that transform the data, you can chain them together and use it for different services. So you can reuse the code, because adding code dependency is less expensive than adding data dependency. And also leverage the partition and data locality as much as possible, because this really helps to get your job done fast. So that was about the technology stack, and I also wanted to give you an overview of what is the team behind it. So this is the Quby team, and the name of the team already tells a lot. So we are the United Data team. So we have all the skills necessary to run this product from the data point of view, from the analytics translators all to the data engineers. So with data scientists and machine learning engineers. And what is the message that I want to bring you is that if you look at what are the responsibilities of this team, we have a big overlap of the skill set. So being one team means that we can share the knowledge much better across the disciplines and get the product delivered end to end. So this is what helps us to be more dynamic. We work in micro teams, so we select few people from across the spectrum for each feature that we deliver, but we work close together. And why we think this is important? Because, of course, we want to work in a healthy and balanced team. This is the first thing. And this is the only way that we see that we can deliver great products and services for our customers. But you don't have to believe only me. I have some paper that back up my opinion. So who of you have read this paper? So the hidden technical debt in a machine learning system? Not many. This guy said that developing and deploying machine learning systems is relatively fast and cheap, but maintaining them over time is difficult and expensive. So among all the reasons that they have to believe that, there is also something regarding the team. So they said that cultural debt is one of those things. So keeping two separate teams for data engineering and data science creates this cultural gap between what is being done in the research part and what is done on the engineering part. So a way to mitigate it is to create teams that are strong both on ML research and engineering. And this is why we wanted to create a happy team where everyone can work together. So you see there's no boxes anymore in the picture. Let me close the talk with what I started with. So if we really want to reduce the energy consumption and we look into our data, what we see is that in the last 12 months, we have detected with our algorithms 87 million inefficient appliance cycles in the homes that we monitor. And if only these appliances were run efficiently, which means that maybe instead of washing at 90 degrees, people wash it at 30, we could have saved 67 million kilowatt hours of energy. And in the last 8 weeks, which was not even that cold, we have noticed that there was more than 700,000 cubic meter of gas used in houses while we didn't detect any activity in the house. So it might be that people were not at home, and this is the amount of gas that we could have saved in our user base. So step by step, we are trying to enable this transition and to go to a more sustainable future. And that's all from my side. Thank you very much.